So I'm Alan Walden. I teach mathematics at Highline. Michelle Jensen is in my second quarter calculus class this quarter, and we're doing trig substitutions and so forth this week. So, Michelle, I thought I knew what you were going to talk about, but I guess with a title like Math is Everywhere, it could include almost anything, and I'm sure she'll let you know.
Yes.
Exactly what it is. Michelle's been one of the bright spots in our calculus sequence since, well, I had her in first quarter pre-calculus 1 last quarter, and now in second quarter calculus, and in a room where which is mostly guys, mostly wearing black and gray. Michelle is truly a bright spot. Michelle Jensen.
Okay, so my name is Michelle Jensen, and I'm a Running Start student here at Highline. Kind of what I'm going to talk about is I'm going to take you through my thought process and where I've been at the last 2 quarters, not just in my coursework, but outside of class as well. So I'm a math major, and I want to be a high school math teacher. And teaching is something that's always really fascinated me. I've always had a really high respect and admiration for people who teach. One of the main reasons I decided to do Running Start was because a lot of the teachers at my high school treated math and any subject like it was a chore or a job that they had to do instead of something that they genuinely loved and cared about and wanted to share with the classroom. And that caused me to beg the question, when teachers appear uninterested in their own subject, how can students be expected to be interested in what they're teaching? So over the course of last quarter and this quarter, I've begun to look at students' interest levels in specifically math. And I've noticed that they're pretty low, at least from everybody I've talked to. All my friends will go, "Oh, so what's your major?" And I say, "Math." And they say, "Oh, I hate math." And I say, "Okay, did I ask you if you cared about math?" Like, people are so open to sharing their aversion to math, and it makes me really, really sad. So one of the things that I've started to look at is how I, as a math teacher, could make math more fun and interesting to students. So that's what this is all of my thoughts on math. And one of the things that I came across in my research is the fact that math is everywhere. Everywhere. So I posed a Facebook survey to my friends, and I asked them these 3 questions. If they liked math, and then fill in the blank, I like math when, and then anything else they wanted to say about math. And the results were pretty astonishing. 11 out of 16 people said they didn't like math. Big surprise. 5 people actually used the words, "I hate math." Only 5 people said they liked it, and 2 of those were math teachers. So they don't really count. I got a few interesting answers for B. A lot of them said, "I like math when never." I like math when class is canceled, when I don't have to do it, or when I count my money. And then other comments included that math was too unforgiving, and if you screw up, 1 step in the beginning of the problem, then it ruins your answer in the end. And that's just not quite fair. A lot of other comments said if I had a better teacher, I would have understood it, and I didn't understand it in the beginning, so I couldn't understand it for the whole rest of the class. So obviously there isn't too high of an interest in math. To each person who took this survey, I asked them a follow-up question. I asked them why they didn't like math. And a lot of them said, "Oh, I don't understand it." But a lot of people said it was boring and that they didn't see how it applied to their life. And this part really confused me because I myself am a big math enthusiast. I love math. And there's so many ways that math is fun and math is exciting and it's applicable that students don't know about. So let's start looking at this. Let's play with some numbers. Let's just add, let's take 0 and 1. That's 1. Now let's take the last 2 numbers in that sequence and add those together, and that's 2. Let's do it again. Is anybody seeing a pattern? I'm seeing my favorite number series, the Fibonacci numbers. And Fibonacci numbers have a lot of cool properties. One being the Fibonacci number spiral. This looks familiar to people, I'm assuming. So we take this, or we get this by taking the square of, I put the sequence down here at the bottom. And if we take so we take a 1 by 1 square next to a 1 by 1 square next to a 2 by 2 square, and etc. And when you connect the corners of the boxes in a curved line, you get this big spiral. So, alrighty. Okay, so we have this spiral. What are some other cool properties of Fibonacci numbers? So, let's do some division now. So what happens if we divide one Fibonacci number by the previous Fibonacci number? So I did all this, and I've noticed that as we get into the bigger and bigger numbers, we start approaching this number 1.618 something. And if we keep doing this and we keep dividing more and more numbers, we approach the number 5, which is an irrational number, kind of like pi. It just keeps going and going and going. But it's a really special number. So where else does it show up? And there's many ways to approach getting the number 5, so let's look at another one. So if we take a line A and we divide it at the perfect place so that the ratio of A to B is the same as B to A, this only happens in one special place, and that is when A is phi times the size of B, and B is phi times the size of C. So this is one reason that phi is called the golden ratio. This can also be seen in a rectangle. So if we take, here's our big line segment, there's our bigger line, so this bigger segment, smaller segment, and A plus B, the full length over A is equal to A over B, which is equal to phi. This is another reason that phi is called the golden ratio. It's also called the golden rectangle. Yes. Okay. And so notice how when we cut this into a square, we're left with another rectangle. And then if we cut another square off of that, we'd have another rectangle. And if we cut another square after that, we'd have another rectangle. I'm going somewhere with this. Okay. So you can also see golden rectangles in the Fibonacci number spiral. So we have our big rectangle, and then we cut one off, and there's another rectangle, and we cut one off, and there's another rectangle. So golden rectangles everywhere. And the reason this happens is because when we divide the Fibonacci numbers, we approach phi. So the bigger your Fibonacci numbers are, the more accurate your decimal is going to be in terms of phi. And the bigger your picture is, if we put 21 and 34 and 55, all the big squares, your golden rectangles would become more accurate in terms of phi as well. Okay, cool. So now we have a spiral, we have a golden ratio, and a golden rectangle. But why does this matter? Where can it apply to my life? So the golden ratio, we see this all throughout our everyday lives, whether it be in pivotal parts of it or the really little minute details that we don't care about. The golden ratio is always there. So the golden ratio appears in art. Leonardo da Vinci was a huge fan of the golden ratio. He started looking at the human body and the ratios of lengths of certain body segments to other ones. A lot of them are phi. And so that's why he called it the divine proportion. And he also, Leonardo was a mathematician. He liked to incorporate math into his art. So if you take a closer look at the Mona Lisa, if we connected this, we'd have, so this is the Fibonacci, if we connected this, we'd have a big spiral. And if you notice that where the golden rectangle, the edges outline her face and her nose and her eyes, really the pivotal, the most focal points of this art piece. So the next place, so phi is almost omnipresent in nature, and this is the really cool one to me. So I mean, you can see where you see the spiral in nautilus shells and hurricanes and galaxies. You can see the spiral here. But what about these? Why are there spirals in pine cones and flowers? And this was really interesting to me. So let's back up a little bit. Plants photosynthesize to make energy so that they can grow. So if you're a plant, you're going to want to grow in a way that optimizes the amount of sunlight that you can receive. So we grow our first little petal right here. Now, we want to grow at a rotational distance. We want to grow our next petal so that it doesn't overlap with this one. Because then say if we do 180, then we're right back here, and we're covering up our first petal. So that one doesn't get any sunlight. So what is the angle here to make a perfect rotational distance so that it won't overlap? So let's see, if we picked another one, say we do this, then we just start filling in these bubbles, and then we run out of space anyways and we start overlapping. So say we wanted to make the fraction really, really small and just keep doing this and this and this and this, well then you have all of this overlap and you've wasted all the space over here. So so if you were to divide, 360, a full rotation, by any whole number, you'd always get overlap. So what if we used an irrational number, like pi? See where I'm going with this? So if we did 360 over 5, you get approximately 222.5 degrees. That's the bigger one. There's also 137.5 degrees. That would be the smaller one. So now let me look at my picture for this one. Okay. So now this is where it gets cool. So if we were to draw, here's our first petal. Stick with me, I'm a bad artist. So if we drew our next one 137 degrees this way, we go here, and then about there, and then we're here, and then we're here, and we're here, and we're here, and we're here, and we're here. So anybody notice anything with this flower in particular? I see a spiral here, here, here. So we see spirals in this one as well. So now let's go back over to this picture. And let's count how many spirals are in this pine cone. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 red ones. And 1, 2, 3, 4, 5, 6, 7, 8 green ones. Okay. And now these ones, I'm just kidding, we're not going to count all those out. I've already counted those, that's 21 and 34. So 8, 13, 21, 34. Where have I seen these numbers before? Fibonacci sequence, right? So we phi distance apart and Fibonacci numbers in our spirals, and that's all because when you divide the Fibonacci numbers, we approach phi. It's just so awesome. Okay. So phi has also been known to play a pivotal role in determining beauty. This is Florence Colgate. She is Britain's 2012 most beautiful face. And why is that? Well, if you look at the ratios from one segment of her face to another segment of her face, her eyes to her nose flare is 5 times the nose flare to her base. So this is all the golden ratio here, all of that. And what advertisers have done is they have taken all of these golden ratios and they've made the Marquardt beauty mask. So this is mathematically the most beautiful face there could possibly be. Isn't it gorgeous? So what advertisers have done is they take this mask and they Photoshop their models to make their face look exactly like it. So anyone can look beautiful with math. So similar to the beauty aspect, advertisers have taken the golden ratio to use for their product manufacturing. So the more golden ratios there is in a product, supposedly the more people are going to want to buy it. And we can see this in the iPhone, in Toyota's logo, Pepsi bottles, Atari's logo, Hyundai's logo. Hotel Indigo has a spiral in their logo. Now, who can see phi in Disney's logo? I got the I and the Y. We have uppercase and lowercase phi right here. Okay. So math really is everywhere, right? I mean, even our beloved president has phi in his signature. Whether that's actually intentional or not, I don't know. I just thought it was too funny not to include. So math really is everywhere. It's in art, it's in nature, beauty, product design, and it's so fascinating. And this is the kind of stuff that we should be teaching students and we should be showing students to encourage and inspire interest in them. One mathematician, Arthur Benjamin, who also teaches mathematics at Harvey Mudd College, has said that there are 3 parts to math. There's calculation, application, and inspiration. And most of the focus is put on calculation because, I mean, it is important. But we can't forget about inspiration. I mean, we can know how to do all the calculations in the world, but it's not going to have any purpose if we don't have the inspiration to know what to do with it. So it's important that we show students how to calculate, but it's also important to show students why we're learning these calculations. Or in the words of Arthur Benjamin, it's not just about solving for X, it's about figuring out why. Thank you.